Okay, so I just handed back some homeworks, and I don't know if I mentioned this last time or not, but the homework assignment that's due today was I think it was a call by value.
Call by reference or something?
Call by value, but anyway, it'll be due tomorrow. Okay, so what we'll do is we will finish up doing flow of control.
I never wrote it up.
We'll finish doing flow of control. That's what you get for not doing it on the simulator in the first place. So
Can I get half credit?
sure, if you'll write it up and test it. You need to test it with the unit with the. Oh no! Wait, wrong class.
No, yeah.
Wrong class. Yeah, right. I momentarily switched to computer systems. Okay, so what we'll do today is we will go over the for loop and talk a little bit more about flow of control, and I think we'll be able to get to the material that maybe or maybe not to do the homework problem for tomorrow. But if not, it's still due tomorrow. Okay, so I think at the end of class last time we mentioned a little bit about what is involved in a for loop. So basically you have these, 5 things. You have to initialize the control variable, then you have to test it. The test is at the top of the loop. Then you execute the loop body, and then the thing about the for loop is that there's another little additional thing that typically affects the control variable, and you do that at the bottom of the body of the loop, and then you branch back up to the test that's at the top. And the example that we're going to do is this one that is just a little nonsense example to print out some integers. Okay? So I think what we should do, this is figure 6.14. So I think what let's do is it's over here on the board. We'll keep this, we'll look at this, and let's just do the first few, see if we see how to translate this for statement, all right? So what's always the first statement?
Branch.
To?
Main.
All right, now, let me see. What kind of, we have locals, right? So how do we do, in fact, I guess there's just one local, huh? So how do we do, so that local is going to be where? On top of the runtime stack. So how do we do J? Because it's local. What do you,
Dot equate 0.
Yeah, dot equate, and then the offset. So this would be dot equate 0. And this is, what will our,
We're going to say
it'll
local
be,
variable.
local variable,
pound 2D.
pound 2D. And then, is that it?
Now we have to stack pointer.
Yeah, so here's main.
Yeah.
And then how do we actually allocate? Exact.
Sub SP.
Sub SP, how much? 2, because it's an integer. Immediate. And here is our
Allocate.
allocate pound J. Okay, are we good? Now comes the for statement. So what is a for statement? It has 3 little compartments. The first compartment is the initialization that happens once.
So we just did that.
So we need to do J, what does it say? J gets, yeah, so J gets 0. So what do I do? J gets 0. Load accumulator, 0, immediate, and then store accumulator, J, stack relative. Is everybody clear on that?
Yeah.
So this happens once at the beginning, and this is not, and now comes the test for the loop, right? So let's put for the test, let's just say for, even though this, technically this is the for, but, I mean, but we'll just, this label, because this is the for test. Maybe we should say for test, whatever. Now, what is the test? The test is J is less than 3.
So you want to compare? So we do load.
So, well, now, see, it's a little, should we optimize or not?
We need to load J. No.
Well, I know, but see, the thing of it is that we're going to be coming back from up here.
Right.
Well, let's not optimize, and then we'll see how to optimize. Okay. Okay. So if we don't optimize, what do we do? Load accumulator, J, stack relative, and then compare accumulator, 3, immediate. Okay. So now it's if J is less than 3, we do it, right?
So we branch with
So we branch out of the loop on what?
Less, oh,
Greater
greater
than
than.
Greater than or equal to.
So BRGE to what? N4, something like that? Is everybody good so far?
And that's always immediate, so we don't have to write it.
And that's always immediate, so we don't have to write the addressing mode for the branch.
string output.
And then stro, is it stro?
That's-
Oh, J equals, yeah. Stro,
Oh, yes.
message 1, direct,
Deso.
and then
Yeah.
J.
deso for the J,
That's it.
And then stack relative.
deso J stack relative,
And 4.
and then here's our N4. Oh, no, not N4 yet, because what do we have to do? Now we have to, because the last compartment is J++.
Oh, we have to do bash in.
Oh, we didn't do the bash n either. So,
Caro
Caro,
and like.
bash n immediate.
So now we load the.
And now you want to not optimize? Geez, this time, well, okay, let's not optimize. I think the code's going to be optimized a little bit.
That's okay.
So load accumulator,
J.
J, stack relative,
Add the accumulator. 1 immediate.
add accumulator, 1 immediate is correct.
Store accumulator. J.
Okay, anyone else want to chime in here? Store accumulator, J,
She's just too fast for us.
yeah, she is too fast. Okay, stack relative.
And 4.
And now,
No, we have to
no,
branch
and
to
now we branch up to the test, right?
Yes.
So branch to 4.
Oh, yeah, that's a lot of loaded accumulators.
Hmm?
That's a lot of load accumulators.
It is. I think that we should optimize this a little bit. And now, if this test, it comes down to here, right?
Yeah.
So now is our N4.
string output.
And do we have another string output? Oh, yeah. STRO, blah, blah, blah. Okay,
And then
so,
we need a, add SP at the end, right?
and an add SP, blah, blah, blah. Okay, so let's see if our blah, blah, blah stuff, let's see how it all works. Are you ready for this? Boom. Did we do it, right? Somebody check us out here.
We just optimized by taking that first load.
So yeah, how did this code here in the figure in the book, how did that optimize?
It took the load accumulator off that.
This one here?
So it was already loaded with.
Yeah, because now, yeah, you see, yeah, that's interesting because, but you have to, there's 2 ways to get here. We can get here from the top or we can get here from the bottom.
But we have the load accumulator down there.
But we, yeah, right. Did it optimize any of this? How about this load? Did it optimize this load?
No.
No.
That one's there? Okay, so you could optimize, so this is partially optimized. But now we know the concept of optimization. We can understand what's going on, right?
You just have to be careful that you check both cases.
Yeah,
there.
yeah, and now look, you guys, you have to, the compiler would have to know that too when it does these loops, right? It would have to say, oh, that's the current value, oh, that's the current value.
Oh, wow.
But it can do it. It can do it. So here is the, and then there's the add SP at the end to deallocate pound J, okay? So here is the, the branches. See how you have this condition, and then that branches to S3, and then at the end that branches up to S2. Are you with me? And then otherwise it goes to S4. Now, you guys, what do these arrows look like?
Pointers.
Well, yeah, they. but these arrows do not indicate. Well, I guess they do indicate addresses because it's the address of the instruction to execute next. So yeah, they are pointers. I guess they are.
What was the other answer?
Well, I wasn't thinking about data because these are instructions.
All right.
See, I mean, normally you think of pointers as a pointing to data, but
Well-
these pointers are pointing to instructions that are going to be executed next.
Wait,
But
Are you with me?
Treated as data.
Is this not?
I don't think that's right.
You don't think this is right?
Shouldn't the top one be pointing to S4? out of the for loop, not inside the for loop. Right? Because the bottom one
Why does it
repeats
branch?
the
Oh, you are right, you are right. This is not a picture, yeah,
Not a before.
this is not a picture of a for loop. Ah, yes, which is my point.
Oh.
Okay, yeah, right, okay, yeah, you're right. Yeah, sorry, I interpreted this figure incorrectly. This figure is not the for, is not how, I mean, you could do how the for one, it's just like the while, right?
Yeah.
Okay, but now, now what does figure 615 represent? Figure 615 represents the following. Do you see that if we're not talking about compilers and how compilers translate loops and if statements, do you see that it would be possible if you just write straight in assembly language, that it would be possible for you to have, there's nothing to prevent you from writing code like this figure 6.15. Do you see what I mean? There's nothing to prevent you from testing a condition, and if that condition is true, going to S3, and if it's not true, going to S2. But then, after S3, you test condition C2, and if C2 is true, you go up to S2. Are you with me? There's nothing to prevent you from writing that directly in assembly language. Yeah? Now, here's my question. Does this correspond to anything, any statement that you can write in C++? Because, I mean, there is some kind of a loop somehow, I mean, but it's testing, I mean, is the test at the top or at the bottom? There's two conditions. You're going into the middle. You're branching up to somewhere in the middle of the loop and da-da-da. Are you with me? So, it appears that this code does not correspond to anything that we can write in C++. Are you with me? But does it?
But.
As a matter of fact, well, no, we're talking about flow of control here.
Oh, that's right.
We are talking about flow of control here. As a matter of fact, I give you a challenge on this next figure. Here is a picture or here is a program that you can actually write up and run it on. And here, that's just the first half. Here's the second half. Now look at you guys. Look at what this figure 6.16. Look at what this figure is doing. It's got deci, and then another deci, and then a load and a compare, and a branch of less than, and then another deci, and then a load and compare. And where are those branching? What are they branching to? L1, L2, L3, L4.
And there's a stop in the middle.
And there's a stop in the middle, and there's a BRLT, and there's, and there's the other stop up there, and blah, 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 blah. Now, you could actually take that code, and everywhere there's a conditional branch or an unconditional branch, you could draw an arrow down and da-da. You see what I'm saying? And what would it look like if you did that? I mean, because there are branches all over the place, and they're going all over the place. What would it look
What's your
like?
analogy from the book?
Yeah. It would look like a bowl of spaghetti, like in figure 6.17. And there's nothing to, and this is a legitimate term, by the way, in computer and software.
Really?
Full of spaghetti?
No, spaghetti code. The phrase spaghetti code. If you talk to
anyone?
talk to a computer science guy and you say, oh, that's just like spaghetti code. Well, actually, it's a little harder. Since most people program in HOL6 languages nowadays, they don't program in assembly language anymore.
So you don't.
I thought that you made that up when I was reading the book.
What, spaghetti code? Did you Google it?
No.
Well, you should have checked me out. You should check out. Google spaghetti. I wonder if it's still Google spaghetti code. See what you come up with. Okay, but look, in contrast to spaghetti code, over in part A of figure 6.17, we have the way you write code in most high-order languages today. Most high-order languages today have if without an else, if with an else. They have whiles, while loops. And furthermore, you can nest any if inside of a while. You can nest any while inside of an if. Are you with me? And if you And if you are limited that way, then your flow is called structured. You see what I mean? Now look on the left. Look, do you see on the left what those brackets on the left-hand side mean? They mean like the outer bracket could be one big loop, or maybe one of those ones could be an if statement. So you can put an if statement or a loop, an if statement or a loop. And you can nest however arbitrary you want, any if inside of a loop, any loop inside of an if, and you can nest multiple times. But whenever you do nesting like this, what's the rule for those brackets on the left-hand side of figure 6.17a? What's the rule for those brackets?
They don't cross.
They don't cross. It's like nesting boxes, you know what I mean? Well, you know a nesting diagram.
Yeah.
Are you with me? So if you program in C++ and the only thing that you do are if statements and loops,
There's no cross.
your code is structured by definition. But what we're just seeing here is that it's possible, if you write in assembly language, to have it not be structured. All right, which brings us to a big major question. Which one limits you, structured or unstructured? Which one limits you?
Structured.
Structured, that limits you. Are you with me? You can do unstructured code writing in assembly language. So here's the question. Do you think that there exists an algorithm that you can implement without the limitation of structured coding?
Yes.
That you can't write with structured coding?
Yes.
In other words, does there exist an algorithm that if you want to implement it, you'd have to do it in assembler because you're not limited to?
I don't think so. There's got to be.
Wait, you said yes or
There's
no?
got to be. No, I didn't understand the question. There's got to be an equivalent in structured code, right?
But it limits you.
In a good way.
Well, yeah, but it still doesn't give you maximum freedom to make the branches wherever you want them to go.
But you could probably do it, it just might take more code.
There'd be more code.
You might have to copy
You'd
and
have to-
save things
You'd have to
other
rework like
places
the
and-
entire program.
To
probably.
really be specific with the contents of each of your if statements and for statements.
Yeah, actually, okay, now here's the next question. You believe that. Do you think that you could prove it mathematically?
Someone.
I
With a
couldn't.
Turing machine?
I'd rather not.
Well, no, not a Turing machine.
You could prove if it could be.
No, actually, Turing machines can be way unstructured because you can go.
Can't you say that any
Tur-
Turing
Tur-
machine can be made into any other? Like if two things are Turing computable, then they're equivalent, and so if you had something.
Well, but the question is structured Turing computer, is everything that we can do is structured, you know, the church
Yeah.
Turing theory.
C++ programs are Turing machines, right?
Well, the answer is yes, but in order to show that, what do you have to prove? What would you have to prove mathematically?
That they
That-
they have
that-
one-to-one correspondence.
Yeah, that any what?
That any spaghetti code.
Any spaghetti code program can be what?
can be made into.
Can be made into, there is an equivalent structured flow of control that will do that. Are you with me? Now, do you suppose anybody has done that?
Yep.
The answer is yes. And you know who? You know who it was?
Dr. Morford.
No, it was Bohm and Jacopini in 1966,
Oh, those are cool guys.
Italian. They proved mathematically that any algorithm containing gotos, now by go, they use the word goto
Instead of branches.
instead of branch, but that's
Yeah.
another phrase for branch. Right? Oh, did you do spaghetti code?
Spaghetti code is a pejorative term for source code that has complex and tangled control structures, especially one using many go-to exceptions, threads, or other unstructured branching constructs.
Yes. Now, here's the thing, you guys. These guys proved mathematically that any algorithm containing gotos, no matter how complicated or unstructured, can be written with only nested if statements and while loops. You only need if and while. Those are the only loops you need.
I think we did learn that in like C++ programming 101. That you can write
That you can write anything. Yeah. Well, this is the mathematics. And you know how they had to do it? They had to give a way to mechanically, show that how these branches, so they analyzed, well, you branched to here. So then you can identify blocks of code in between any branch, and then they had to show how any branch, any kind of branch, either forward or backward, like if you go forward or backward or into, then how that can be mechanically changed to a program that uses only whiles and ifs.
How long was the proof?
Actually, that's a good question. I wish I could say that I've read their proof. I haven't. But it was back in 1966. I'm sure it's a classic. I mean, it's an important theorem. It is called the structured programming theorem, and you should know it.
This is?
This is called the structured programming theorem. You should know what the structured programming theorem is. Early in the days of programming languages, they actually, did you know that C actually has a go-to statement in it?
Ah.
So you can put a little label on a thing and you can go to boom, and you can do it. Because it was way long time ago, it was back in the 60s. And it was the early 70s. Anyway, there was a huge debate on, because you can write any program without go-tos, whether the go-to statement should be in the language. As a matter of fact, the second big historical fact that you should know is you should know about the go-to controversy. Now here's the go-to controversy. Have you heard of Edgar Dijkstra?
Yeah.
Do you remember what he did?
He has an algorithm.
Oh yeah, he does have an algorithm.
Oh, yeah. With,
It's a, what is it? You know what the algorithm is? Dijkstra's, it's a famous algorithm. You should know. Actually, we mentioned this in data structures.
Yeah,
Do you remember? Do you remember what algorithm he has?
do you have to do with trees?
It's graphs, not trees, but graphs. And it's the shortest path.
Oh, is that what it is?
Dijkstra's shortest path algorithm. And not only that, those of you who are in paradigms, do you remember what else he invented? The guy was a genius.
Big.
In concurrency, with concurrency, do you remember what else he invented? Why do we call it P and V? What were P and V?
Processes?
No. Oh, we didn't call them P and V, we called them signal and wait. But we said that originally they were called semaphores.
He did semaphores?
He invented semaphores. And they're typically called P and V because those are the Dutch words for wait and signal.
Okay.
And not only that, but he did this. I actually met him. I shook his hand, this hand right here, at a conference once. Yeah. You'll never be able to do that because these guys are all being deceased. Well, Tony Hoare is still alive. Anyway,
Is he still
the
alive?
Hoare triple, yeah.
Mr. Hoare Triple.
Yeah. But listen to this. What Bowman-Jacopini proved is that it was mathematically possible to write a program without a go-to statement. But what did Dijkstra say? Dijkstra said 2 years later. Dijkstra said, not only is it possible, what did he say? What is his statement? He wrote a famous letter that set off a huge controversy. And I was alive when
He
this.
says it's beneficial.
Yeah, not only is it possible, he says it's beneficial. And he was so dogmatic about it, he said the go-to statement should be banished from all high-order languages. And I just got through saying, C has the go-to statement, so does C++.
C++ has it?
Mm-hmm.
But no one,
But no
we
one
haven't used it
No, we don't teach it. We don't teach you how to use it.
because it's not.
Break is a little bit of a,
Kinda, yeah.
it's kind of like a go-to. When you can break in the middle of a loop. But breaks, they can be good, but some people even argue that you shouldn't use a break.
Is there a way to do
In other words, there's a loop, and then you can break in the middle of a loop. And that I have seen. I'm convinced that occasionally that's really a nice, elegant solution to a problem.
if something happens, just break out of the loop?
Yes. So there's a loop statement that.
There's a place for it.
Yeah. But in that case, the test is neither at the beginning or at the end, but it's in the middle.
Right.
But that's a little bit of a go-to because it's not a while. Because a while, the test is always at the beginning. But anyway, he wrote a paper. Dijkstra wrote a paper. It was published in 1968 in the Communications of the ACM. And when he wrote that letter, in that letter you can read, it's easy to look up, it's a famous classic letter. It set off a huge controversy, and people said, oh, no, you can't shoot. Yes, you should. No, you shouldn't. And what was the big argument over? Even though actually somebody said it here, even somebody mentioned it here. If you make it structured, yeah, you can make it structured, but what might you sacrifice?
Freedom.
Yeah, no, well, freedom. One thing it is, but what did you say? Efficiency, performance. Okay, you might be able with a go-to to write a program that executes faster than if you don't. So a lot of the controversy back then was over performance issues. But ultimately, it raged, and I can remember there were letters after letter. I mean, if you go back and read the debate, it was, and not just hackers, but eminent computer scientists of the day. I mean, it was a radical idea. I can remember well. It was a radical idea at the time, and Pascal. Now I'm trying to remember if the original Pascal might have been a language that does not even have the go-to statement in it. And that was considered radical, in its day. But now the controversy has pretty much died down. But it has important practical ramifications in programming. Do you guys? I should have looked this up before I came to class. Does Python have the go-to statement? Because that's a relatively modern language. I don't think Java does. But of course, you've got this exception handling that you talk about complicated flow of control. You've got the finally and try catch finally.
Oh, yeah.
That's pretty complicated flow of control. So anyway. Well, yeah. Sorry, part of the class has had these courses that are out of sequence, so we are referring to things that some of you haven't heard before. But anyway, now it is pretty much now all of your programming is, we don't teach go-tos anymore, and so you guys have been in your generation. The controversy is kind of non-existent because you have never experienced unstructured flow of control anyway. But it's an important mathematical concept.
Python has it.
Oh, Python does have a go-to? It does.
It also has a come from.
Yeah, right. No.
It does.
No.
Yeah.
Well, okay, let's not get into that. Okay, so moving on. You sure that's not an Onion article?
Entrian.com. I don't know if you've ever heard of that.
How can you force it to come from?
It's a debugging thing.
Oh.
Opposite of go-to.
Oh.
Whenever label X is reached, jump here instead.
That doesn't. Well, anyway, that's a famous old joke.
Really?
The come from statement. Because how can you think about it? You have to go backward. I mean, anyway. Okay, so next thing we want to do is we want to see how functions are called. Now, you remember from our discussion when we reviewed C++, and you had to do all of this runtime stack.
No.
So what happens when you call a function? What are the four things?
No, that's the
That's the
return value,
storage for the return value,
parameters, storage for the parameters,
the parameters themselves.
storage for the return address,
No, and the return address itself,
and then space for the local.
and then storage for the locals. So the third thing was what? The return address. So in the PEP8 instruction set, there is an instruction whose mnemonic is call. Okay, and at the assembly language level, these are called subroutines. Okay? And here's the semantics of the call subroutine. And you see that it has an instruction specifier of 0001, 011A. So what do you suppose this A is? That's an addressing mode. Do you remember the addressing mode for the branch instructions?
It was 0 or
Immediate
1.
or?
Either
indexed?
immediate or indexed. It's the same thing with this. This is like a branch instruction. In fact, what's this RTL? What's the very last thing that this RTL does?
PC gets operand.
PC gets operand. So because PC gets operand, what does that cause to happen? The next instruction to be executed is the one specified by the operand. So it's like a branch. But the thing about the call is it does something before it does the branch. In fact, it does two things before it does the branch. According to this RTL, what does it do?
It decreases the stack pointer by 2.
It decreases the stack pointer by 2. So here, let's think about it. So here we are on the stack, right? And suppose SP is right here, pointing to this. So the first thing it does is what?
It decreases the stack pointer by 2.
It decreases the stack pointer by 2. So now instead of the stack pointer pointing here, what does it do? It whoosh, points to here, right? Are you with me? And then what does it do, according to that RTL?
Sub stack pointer gets PC.
Ah, so what does it put in here?
Contents of the program counter.
The contents, now what does the program counter contain?
Address of the next.
The address of the instructions
So it's
to be
stored where
executed
it was
next.
before it jumps.
Well, my question is this the incremented, you remember, okay, what's the von Neumann cycle?
That is the increment.
Yeah, because what is the von Neumann cycle?
Fetch.
Fetch, decode,
Execute.
increment. And now this is the execute, right? So what do we increment? The program counter. So therefore, what is this address?
It's gonna be
The next instruction after the call.
Yeah.
After the call. Are you with me? And it's going to put that on the runtime stack. And then what does it do?
PC gets operand.
PC, and then, so this saves saves where we were, and then the program counter gets to where we want to go.
That makes sense.
Doesn't that make sense? And do you see that RTL depends crucially on the what? The von Neumann cycle, which is fetch, decode, increment the program counter, and now when we execute, we're taking that incremented program counter value and putting it here on the runtime stack. And we're pushing it. SP gets SP minus 2. So all that happens in one instruction. These three things all happen in one instruction. Are you with me? And do you see that that's what needs to happen in order to push the return address onto the runtime stack? Well, if there is an instruction that pushes something onto the runtime stack, there must also be an instruction that does what? That pops it off from the runtime stack and assumes that the stack pointer is pointing to a return address and does what? Does the opposite. So what do you suppose that one's called?
Return.
RET. Now, here's the thing about RET. RET actually has 8 versions. There are 8 RET instructions. They are RET 0, RET 1, RET 2, RET 3, RET 4, RET 5, RET 6, and RET 7. And furthermore, is RET unary? See, let's go back and see. Is call unary?
Yeah.
Hmm?
Oh, no.
No, why not? Because operand.
Oh.
It has an operand, yeah? So call is not unary. It has an operand. Because you have to tell, and the call you have to tell where to call,
Where you want to go.
where you want to go. The function,
so
where you want to go
RET is
to.
unary.
But RET is unary.
Because we've already stored.
We've already stored where we want to go. So RET is unary.
Okay.
Now, is that clear? Is everybody clear on that? So what's this extra little n? Well, this instruction does more than just pop the instruction off. What does it do?
stack pointer gets
It's stack pointer plus n. Now, why do you suppose it first does stack pointer gets stack pointer plus n? Because what happened? Because when you return from a function, what do you want to do? What's the first thing you have to do?
The pop,
Pop the what?
the local variable.
The local variables. You have to pop the local variables. Are you with me? So that's what that does. Built into the ret is not only the ability to do this, but if there were some local variables such that the SP, you know, if there were some like local variables here and here such that SP was pointing to here. Are you with me on this figure? Then what this would do is it would do SP gets SP plus, you know, if you did ret 4. You see what I mean? Then what that would do, and say each one of these is 2 bytes, then ret 4, first it would add 4 to SP and put it here, and then this would be pointing to the return address. Are you with me? And then what would it do? And then what does it do? What's the next thing after SP gets SP plus N? Then the program counter gets what?
The memory sub.
Mem sub SP. So now if SP is pointing here, then the program counter would get that, and then what does SP do?
Goes back.
Minus 2 more. So it's where it was. Yeah? Now, does everybody see that sequence? Do you understand that sequence of events? Are we good with this? Okay?
So can you not have more than 8?
That is a really good question. So what? Yeah, and the answer is this is a shortcut for if you have 8 or less bytes on the runtime stack that you want to deallocate.
Otherwise, you have to do it manually.
Otherwise you have to have another instruction. Otherwise it takes 2 instructions. It would take 1 instruction to add SP 12 or however many, and then ret 0.
Or any combination?
Or some combination, yeah. But I mean, yeah.
Okay.
But that was a really good, that was a great observation, because this would seem to limit you to only having 8 bytes of local variables on the runtime stack. But you can have more, but if you do, then the compiler has to generate an extra instruction.
Is having 8 different return ones, is that specific to PEP 8, or is that?
Yes, it's way specific to PEP 8.
Okay. Cool.
Yeah. In fact, those of you who are in computer organization, you'll see how this happens in a RISC machine. PEP 8 is more stuff that people, yeah. But to answer your question, but on the other hand, it's typical. The instruction set is specific to PEP 8, but it's typical of instructions that are commonly executed, because by far, how many bytes of local variables do you think is typical in a typical function call? If you took a look at a huge program and look at all the functions, all the methods, how many of them do you think would have local variables? Yeah, a whole lot of them have none, 1 or 2 local variables, maybe just a little bit. So this for efficiency, this covers 90% of, but you have to be able to allow for more. I mean, it has to be possible to do more. Okay, so now with those 2 statements in mind, let's see if we can translate this. Let's see if we can translate this program. Okay, so here is a program that has a void function. It's called print try, and do you see what print try does? It prints a little triangle of asterisks. Are you with me? So now let's see if we can translate this. So here we go. First thing we always do is what? Branch to main.
Do we have any globals? No.
We have any globals? No. But what do we have? we have a function called print try. So here what we're going to do is we'll label it like this. Print try. And this will be the first statement of print try. Are you with me? Now, we can start writing the statements for print try, but I think it's sometimes easier to visualize what's going on if we start writing the statements for main first, and then go back and write the statements for print try. Because the first instruction that's going to happen is main, right? I mean, is this one here. Now what is the first statement of main?
Print try.
It's a call to print try. So what do you think we should do? What do you think we should do here? Yeah, we just do call
Oh, call.
print try. Now, what will call print try do? It will, yeah, because what is print try? Print try it's the symbol. What is the definition of a symbol? The symbol, the value of a symbol is the what?
The address.
Is the address of where the code is. So if we say call print try, then the operand will go into the program counter, and furthermore, the next one will be here. Okay. So then what will this print try? So then what will this print try be? Now let's do print try.
Caro?
So Caro.
Star.
Yeah. Yeah, you want to do Strohs or?
Let's do Caro for the first line.
All right.
So then we're going to do two.
Yeah, but then we'd have to do two. Oh, well, yeah, it's a matter of style, right? I mean, Caro, star, what? Immediate, and then what?
Caro bash enemy.
Yeah, Caro, bash, and immediate. You want to just do a bunch of Caros? And then let's just do blah, 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 blah. All right? We could do some Strohs here. We could have them do all Strohs or the first Caro, and let's do Strohs, whatever. Okay, but anyway, the last thing here is going to be what?
Return.
What was the mnemonic?
RET.
And how many locals?
Zero.
No, so it's ret, so this would just be ret 0. All right? And then what will happen is we'll come back here, and then the next one will be what?
Call print try.
Call print try again. That's it.
That's cool.
All right? So here's the, how did we do it here with Strohs? Oh yeah, just to keep them all consistent, we did Strohs for all of them. Does everybody see how the code works?
Nice style.
So print try, yeah, a little style. Programming with style. And then the ret 0, but let's just call print try, call print try, call print try, stop.in.
Do we need to have
Main, yeah?
the comments that you had before your...
Well, you know, I do this on all of these examples to show the correspondence with the corresponding
Code.
C++ code, just to show you how the C++ code gets translated. Are we good?
Yep.
Does everybody see how that works? And so here's a picture of the actual values of the program counter. Right? So look at the program counter before creation of the first call. The program counter, how do we know that the program counter is 0, 0? Oh, I should have asked you this before I flashed that up there. Look, what is the, here, let's see if we can see this. On main, in the main program, what is the value of the program counter just before
The next call.
the first call to print try? Where is that instruction? That's at 001F, which means that when you increment the program counter, what will it be? 0022. Are you with me? So that means that when we execute the call, the program counter has 0022 and the stack pointer is at FBCF. Are you with me?
Right.
Then after you execute it, the 0022 is what's on the stack. Now does everybody see how to read that? From this listing. Are you with me? All right. And then this is just before the execution of ret 0. Now how do we know what the value of the program counter is just before the first execution of ret 0?
Right below the red 0.
it's been, it has been incremented
So 0016.
to 0016. Are you with me? So here, that's why there's a 0016 is in the program counter. But then when we do ret 0, what does it do? What happens to that 0016? It gets wiped out. And now the program counter has 0022 in it, which means the instruction to happen next is the second, is the address of the second call to print try. Are you with me? And that's how it gets, that's how the hardware does the return address on the runtime stack. So what you have to do for tomorrow is you have to do a function that has parameters on the parameter list. Now I think you can read that material, now that we've done this call, I think you can read that material. It's pretty easy to, should be pretty easy to follow. We'll go over it in class at the beginning of class next time, but your homework is still due tomorrow. But, you know, as usual, you know, midnight. Okay, are we good? All right, see you tomorrow.